Hello, we are the team working with Groundwork Bridgeport. I'm Joseph, and our team consists of Fuyuki and Francy. This project is part of a collaboration with Groundwork Bridgeport, a nonprofit that works to revitalize neglected spaces in the city through green initiatives. Our project focuses on two main questions. First, how can we analyze the urban tree canopy of Bridgeport, Connecticut using satellite imagery? And second, how can we explore potential relationships between tree cover and demographic trends? We care because disparities in tree cover aren't just about aesthetics, they directly impact the health and environmental justice of people living there. Bridgeport has only about 20% tree canopy citywide. Low income areas have 54% tree cover, less than wealthier neighborhoods, leading to more heat exposure, worse air quality, and fewer mental health benefits. Trees also reduce runoff in cool buildings, making them critical infrastructure, not just greenery. To address this, we used a range of spatial data sets in Google Earth Engine. This includes Sentinel-2 imagery and NAIP imagery, Copernicus land cover maps, and census demographic data. We structured our work around four main tasks: data research and collection, model exploration and refinement, and finally, temporal analysis to compare canopy change over time. Our first step was improving how we detect tree canopy. We first began with a basic model using NDVI greater than or equal to 0.6, which overestimated tree cover by including grass and other vegetation. We refined this by combining NDVI and NWI to exclude water and adding masking for the ESA world cover dataset to remove any grass. We also incorporated pixel-level texture to better capture dense tree patches, leading to a more accurate tree canopy mask. Once we had a reliable model, we analyzed tree cover at the census block level. We found wide disparities. Some blocks had as little as 0 to 10% canopy, while others reached over 40 to 50%. These differences often aligned with income and density, reinforcing the idea of green inequity. By working at the block level, we're able to generate actionable insights that can help groundwork target areas in need for new trees. Next, I'll pass it along to my team member, Francy, to talk about our tree canopy height analysis.
We also analyze canopy height trend. We use an open source model developed by Meta AI to predict canopy height from an AI imagery, which is also from 3E as specific latitude, longitude coordinates. And then we selected 2006, 2016, and 2023 based on better image quality for prediction and analysis. And after we got the predicted data from the models, first we conducted a time series analysis based on the summary statistics and the below two figures, the histograms and the box plots. We can conclude that for canopy height in terms of mean, medians, quartiles, range, and maximums, 2023 is greater than 2016, also greater than 2006. This result aligns with our expectation that we expect tree growth yearly and the variation also increases over time. Second, we use our data to perform spatial analysis. Based on the three figures below, red points represent positive canopy height trend, and the blue points represent negative canopy height trend. And we can see a clear pattern among three figures that the canopy height increase around outer areas and the canopy height decrease around central areas. This pattern aligns with the satellite image and our expectations because for the outer parts of the image, there are suburbs and we expect growth in suburbs. And for the central part, it is a downtowns and we expect reduction in downtown. Lastly, we use our predicted data to perform Marron's I and LISA analysis, which is local indicator of spatial associations. Marron's I is a scalar to evaluate global spatial autocorrelations, and if its value is greater than 0 and close to 1, it indicates a strong global spatial autocorrelation within the data sets, and we get 0.626. So we can conclude that there is a strong patterns in Bridgeport. And we also did LIS8. This is a local version of Marron's I, and we can use this to conduct cold spot and hotspot analysis. LIS8 is calculated for every points and by comparing with their corresponding neighbors. And for the figures on the right side, the red square represents a value change from high to high, which is a hotspot, and the blue square represents a value change from low to low, which is a cold spot. So based on LISA, we identify hotspots are around northeastern suburbs, and the cold spots are around southwest and central urban areas. So this finding highlights a clear spatial pattern of canopy height trend in Bridgeport. So that's all of my findings. Next, my teammate Fuyuki will introduce tree canopy equity.
Thank you, Francy. In my part, I'll share what we found when comparing the tree canopy to key social indicators across Bridgeport. We started with a big goal to understand how tree canopy has changed in Bridgeport and how those changes relate to demographic trends over time. But when we looked at the data, we ran into a problem. Tree canopy data from different years didn't match consistently. For example, between 2021 and 2023, there was only about 6% overlap, based on a jagged similarity measure using 5-meter grid cells. This means the same areas were not always labeled as canopy, which made year-to-year comparison unreliable. Because of this inconsistency, we adjusted our approach. Rather than analyzing change over time, we refocused the project on a more reliable single-year analysis using the 2023 data. Using 2023 canopy points, we looked at two things: how much coverage each tract had, and how tall the trees were on average. We found a clear spatial pattern. Both coverage and height were lower in the city center and higher in the outer neighborhoods. We expected to see differences by race. However, in Bridgeport, we actually found no strong correlation between canopy share and the racial makeup of a tract. Even the highest correlation with white share wasn't statistically significant. But when we looked at the poverty, the signal was clear. Tracts with higher poverty rates tended to have less tree canopy. Tracts with higher poverty rates tended to have less canopy. We found a moderate negative correlation around 0.5 with a very small p-value, indicating statistical significance. This highlights how access to green space can be deeply unequal and linked to socioeconomic conditions. We saw a similar pattern with education. Tracts with lower levels of educational attainment, especially fewer high school graduates, had lower canopy coverage. The correlation with high school graduation rates was positive and even stronger. The coefficient was about 0.55, and the p-value was also very small, statistically significant. So, while race wasn't a strong predictor here, these socioeconomic indicators clearly matter. There's a lot more we could do with the work. First, we want to improve canopy detection using better saturated imagery, better processing, and better models. Second, we hope to return to time-based analysis once we have more consistent historical data. And third, we are planning to explore advanced methods like spatial regression to get a better understanding of where tree access is most unequal and why. Thank you.